Okay, so good morning, everyone. My name is Xiaoyi Lu. I'm a research scientist from The Ohio State University. So yesterday, I gave a talk about the cloud computing. So today, I'll give this new work. Recently, we start for accelerating big data analytics with NVM-aware RDMA communication protocols. Okay, so in big data processing areas, there's so many requirements about the speed for your processing, for your storage, and others. So the most popular stack being used for big data processing is the Hadoop ecosystem, software libraries, or our Spark kind of things. So for example, if you want to run some batch jobs, you probably use Hadoop MapReduce, and if you want to run some iterative or interactive jobs, you probably will run with Spark. For your queries, you probably will use HBase, and then all of this will run on top of HDFS, which is a fault-tolerant file systems. So the underlying HDFS will be used by all of these upper-level middleware. These models are very scalable, but it also has a lot of communication and I/O requirements. This can be further optimized. That's what we believe NVRAM could be heavily used in this whole stack. So for the modern HPC or data center architectures, there are a lot of drivers for driving technologies to make it great. For example, multiple medical technologies, accelerators, RDMA, InfiniBand, Rocky. Another important thing is NVRAM or NVMe SSD. This is also picking up. So before I want to discuss about the NVRAM, I just want to say that as a researcher or developer, I want to first share how we understand the NVRAM and how NVRAM can work with RDMA from our perspective. Okay. So the first thing is NVRAM give you a lot of good features. For example, its performance is very good compared with SSD or NVMe SSD. It's but a little bit lower than DRAM maybe. But it also gives you very good features like byte-Addressability as well as persistency. So that's why we believe for these big data stacks, this persistency and the byte-Addressability can be really, really helpful. Okay. So with this, we also agree with Tom. This NVRAM technology could be used for storage technology quite a bit. So actually, before I talk here, like 2 weeks back, I presented this similar talk in the UCSD for the NVRAM workshop. Actually, what I learned from there is similarly, many researchers actually don't have the hardware access. I also don't have. Okay, so when we start this work, we are thinking, okay, how to do our research or how to play with it. Then we do a lot of surveys, read a bunch of papers, just try to summarize what kind of techniques they are using to emulate NVRAM on their systems. So broadly, actually, you can divide into 2 groups if you don't have the real hardware. Okay, one group is following the latency model. Under the latency model, they have like different branches. For example, somebody has some hardware-based emulator. Somebody uses software-based created delays to do the emulation. And for the software-created emulation, the people can try byte-addressable memory, add a delay on the flash, for example, your cache line flash. Or they could also use block-based I/O and add delay on your sync. That's a latency model. And then somebody also uses some kind of throughput model. Okay, similarly, you can use both hardware or software approach. So for the basic, if a summary for the latency model, what people did is, for example, they say you want to emulate this PCM or PCM disk. So whenever you are going to access the PCM device, okay, for example, you do memory copy, some kind of things, and then when you do a cache line flash, you plus some extra delay for that. Or when you do msync, plus some extra delay for that. So the delay will be inserted by a spin loop or no ops. So some example studies like a Memcached library, which is a very popular library, or PCM simulator. For the throughput model is a little bit different. They're trying to shorten the bandwidth of inserting delays. So this is the equation of how much delay you have to add it. So the similar approach like a spin loop or no ops to be added. So Memcached this PCM disk library actually is using this approach. To be more clear, so if you want to do NVRAM emulation on top of DRAM, there are 2 popular ways. Okay, one is like you can use PCM disk kind of approach, just like a NVRAM, like RAM disk backed by NVM. So for the applications, you can use mmap, mmcopy, or mthink, or even open write read kind of file system calls. Or another hand is if you want to use the memory semantic, you can use like Tom also mentioned like a persistent memory library. You can do persistent memory copy or persistent, and then this middleware or this library will take care of the your persistency, like CR flash, blah blah. And then we actually did some enhancement on that so that you can emulate the NVRAM performance. So after we did these studies, let's take a look at the basic performance on single node. Okay, so for example, you want to do some kind of copies from DRAM to DRAM, DRAM to DRAM with flash, and then PCM memory latency model or PCM memory throughput model I just mentioned earlier, or you want to do RAM disk to RAM disk or PCM to PCM disk. And here we use some, after our survey, for PCM write delay, we add like 150 nanosecond. For PCM read delay, we add 50 nanosecond, as long as we see you're going to do the persistency. So the PCM memory library, we are using the PMEM, that is open source NVM library. People can download and try. And also we are using the Memcached PCM disk library to evaluate the PCM disk. So what we see is definitely the DRAM volatile, the bottom line here, that's the best performance, but you lose of the persistency, right? And then next one is RAM disk. After that is the DRAM plus CR flash. And then on top of that is like a PCM memory latency, PCM throughput, or PCM disk. So what we see that for PCM disk and the PCM memory latency models will show like around more than 6x overhead compared to RAM disk, we think. Okay, so just like Tom also mentioned earlier, so if you only do one node things is not something important for big data workloads, because you have to guarantee that your data is being replicated across a lot of nodes. Okay, so if you want to do the replication or something like that, you need to use the high performance interconnects a lot. So that's why in this community, the RDMA technology can be heavily used with NVRAM system. So in our group, like I think in the first day we presented the HiPD project. We have done a lot of studies like RDMA Hadoop, RDMA Spark, RDMA HBase, blah, blah. All these things is based on RDMA plus DRAM semantic, okay? We see a lot of benefits, but the problem is how about if NVRAM comes, how you utilize NVRAM plus RDMA to get the optimal performance for these stacks. So with this, we are trying to develop some user level utility library so that when people trying to optimize Hadoop Spark kind of heavy stacks, you're able to use it easily. Don't just go to all the details, RDMA write, RDMA read, commit kind of things. So we want to hide all these details in our NRCL library, which is NVM-aware RDMA communication I/O schemes library. So what's the design scope of that? So basically, but depends on where your data located, you can do 4 types of communication with RDMA in your system. One is DRAM to DRAM, that's obvious. And then the DRAM to NVRAM over RDMA, which means your communication buffers for client are located in DRAM, but the server may use NVM. Similarly, N to D means your buffer for the sender side may in the NVRAM, the destination side in the DRAM. You can probably also do the end-to-end direct RDMA. That is something very interesting. Okay, so then how are we going to design the NRCL library? So basically, we want to do 2 protocols. First thing is like if you have small messages, we still know that for small messages, send and receive maybe should be doing better based on our experience on DRAM. So here what we did is, for example, your application buffer in DRAM or NVRAM, we do a memory copy in the eager header message, and then we send with our header and the payload. And in the receiver side, we get the data and then do memory copy, CR flash, plus the delay to the persistent memory. So in this case, the data will be persistent in NVRAM, and then we send the acknowledgement. This is the send and receive protocol. And then like earlier, Thomas mentioned about RDMA write kind of things, you cannot guarantee the persistency. So here we are trying to use RDMA read. So the idea is that for your data in the sender side, You don't care basically because you may already replicated or you're already persistent. And then in the server side, you send a header into the server, and then server will reserve some NVRAM buffer, and then RDMA read to get the data to the NVRAM buffer, and plus, finally, we need to do a state flush plus the delay to make sure that your data will be persistent in the NVRAM, in the server side. Okay? So these two protocols we designed. Now let's take a look at the basic performance. There's a lot of interesting results here. So we want to compare the communication latency when you use NRCL send and receive semantics first over the InfiniBand and the PCA memory. So there's multiple lines. The first one, of course, the best performance, the DRAM to DRAM performance, but you don't have the persistency. And then after that, you will see like a NVRAM, the worst case of NVM to NVM direct send and receive communication is around 10x overhead. Okay, DRAM to NVRAM we around 8x, and then DRAM to remote NVRAM, NVRAM to remote DRAM is around 4x. Depends on your read-write delay kind of things. But the idea is that if you see this looks like a negative results, right? But the problem is in many big data middleware, you are not going to just store your data in DRAM and done, right? You have to make them persistent. So what they did is they typically spill this data into persistent storage, like SSD. Here we compare it with SSD, NVM SSD. So what we did is, if I get data in DRAM and then I do a memory sync to SSD with different granularity, for example, per cache line, per 4K page or 8K page, we see that if you persist to SSD, it will be much slower than you do NVRAM to NVRAM direct communication over RDMA. That's the send and receive semantic. Then if you see RDMA read-based scheme, you will see similar kind of performance trends. So the NVRAM to NVRAM communication or DRAM to NVRAM communication is still doing much better than you do DRAM to DRAM and then sync to the SSD. So, and also we see that the RDMA read will outperform send and receive for large messages. This is also observed for DRAM to DRAM communication. So now, after we have this library, let's think where are the opportunities you can use NVRAM and the NVRAM plus RDMA inside Hadoop or Spark, this kind of big data ecosystems. Now let's get back to the Hadoop HDFS. So to some of you who may not quite familiar about HDFS, what they did is, so on your client side, you write one file into HDFS, and then HDFS data node will do the replica for you. So typically there's 3 replicas. So which means you have to do the communication, data movement. And your data have to be persistent in the disk by default, okay? Now, if you have to do communication, by default, they're using the Java socket library over TCP/IP stack, which is slow. So that's why RDMA can be used. And the second thing is because you need to do the persistent for your data because of replication, that's typically happened on SSD or HDD. Now if we have NVRAM, we actually can significantly reduce the I/O path, right? I can do communication and I/O together. I can do RDMA over NVRAM and the data already persistent in NVRAM. So then we actually did some study first. For example, if we just blindly run HDFS on top of NVRAM disk, just because with NVRAM disk, you don't have to change HDFS anymore. You don't have to change it at all, actually, because you can directly use it as a RAM disk. So there we see that compared with NVMe SSD, actually, even you have very high performance NVRAM hardware, but your performance may not that good. You only achieve like around 12% improvement. That's not exciting, right? So then we did a lot of detailed studies. We found that, okay, then we need to rethink or redesign the whole HDFS architecture or HDFS write protocol. Then what we propose a new HDFS design called NVFS. That is NVM-aware RDMA, NVM and RDMA-aware HDFS. So what we did is, first of all, we want to, instead of do RDMA over DRAM and then flush to SSD kind of schemes, we do RDMA over NVM directly. And then there's a lot of HDFS I/O operations in big data workloads. So with that, we are trying to explore block access of NVM and also as well as memory access semantic. And then we also propose some hybrid design, like if you have NVRAM SSD, how you can hybrid them together to improve the HDFS I/O. And then because NVRAM is still very expensive, we are trying to co-design with upper layer stacks, so to save your cost. Because big data workloads, you may have a lot of data, which cannot totally save in your NVRAM device. So we need to pick up some kind of important core data into the NVRAM device, something like that. So we have a paper in 2016 ICS for this work. If you have interest, please take a look. Okay, with this, let's take a look at the performance benefit in the HDFS layer or Hadoop MapReduce HBase workloads. So here we compare our NVFS design with the memory I/O mode and the block I/O mode, and compare it with the default HDFS running with IPOB. So we see that if you NVFS memory I/O mode, which has the best performance for test device I/O workloads, this is the throughput. So as we can see, that is the gain around 4x over HDFS. And then for read, it's around 1.2x improvement. And in our cluster, we also did a similar study, the performance like 4x or 2x. So it's very promising results. Like I said, we also designed the co-design with upper layer library like HBase, which run on top of NVFS. So for HBase, we just store the write-ahead log in the NVRAM. What we see that for HDFS YCSP workloads, we are able to improve the performance by 20%, around like that. Okay, that is for HDFS story. Now let's take a look at the even higher stack like MapReduce. So inside MapReduce, where we have the opportunity to use NVRAM and RDMA. So some of you may not be familiar with HDFS. This is the data flow of the HDFS paradigm. So you have the input data, which is a lot of splits, and then you run your maps. Each map will take care of one split, and then you do the shuffle, and then in the reduce phase, you get the data and store to HDFS. So in the shuffle phase, there's a lot of bulk data transfer operations as well as disk operations. Okay, so this means you have a good chance to use RDMA for bulk data transfer, and you have a good chance to use NVM to avoid disk access, right? So that's the opportunity. Currently, in default Hadoop or even Spark, they are using like HTTP-based shuffle over TCP/IP over sockets, or they are using the SSD or HDD kind of hard disk to finish this phase, time-consuming. But if you have NVRAM, this can be easily improved. Okay, now let's take a look how to do that. So I think in our MapReduce RDMA work, what we optimized is when you map phase finished, we use RDMA to get the data into the reduce side, and then we do in-memory kind of operations. So in the reduce side, we don't touch disk at all. So it means all operations in the reduce side already happening in the memory. Okay. So then in that case, NVRAM cannot be used in reduce side. But if we take a look at the map side, there's a speeder in each map tasks and a merger on disk merger. So it means your output of maps will spill to disk, and then you do a like out of core merge sort kind of things. That's a lot of I/O access. Okay, that is very, very slow. And then after that, when you do RDMA communication, your data needs to load back to the main memory and then communicate. That is even slower. So with this, we are thinking there could be a lot of opportunities in the map side to improve the performance with NVRAM. Okay, then what we did is instead of spill your data to the hard disk or SSD, we spill the data to NVRAM. Okay. And then we do the merge sort on top of NVRAM directly. And then when we do the RDMA communication, we use NVRAM directly. So this is some work we have done in SE last year. So let's take a look at the performance. First of all, we show the sort and tera sort numbers. This is very widely used benchmarks to show your MapReduce performance. So there are three bars. The first bar is MapReduce over IPOB protocol. That's, of course, is the worst one. And then RMR is RDMA-based MapReduce with DRAM. Okay, there's no NVRAM. So, but you have to use SSD or hard disk to persist your data during the shuffle phase. And then the third one is our RDMA-based MapReduce on top of NVRAM. As we can see that the RDMA over NVRAM can achieve around 2.3x benefit by map phase compared to the RDMA MapReduce. See here. Right? and also MR over IPOIB. The overall benefit is around 55% compared with MR over IPOIB or MR over RDMA. This is for the sort workloads. And then for tera sort, we see similarly, like a 2.5x kind of performance benefit for map phase, and the overall is kind of 50% improvement. This for sort and tera sort. And then we also try to run some other complex workloads, like Intel high bench workloads. There they have like PageRank, k-means kind of graph, or machine learning workloads. What we see that for sort, we are also achieve similar kind of performance. For PageRank, we can achieve around 21% improvement for 5 million pages. And for k-means, because it's machine learning workloads, it's heavily used, CPU is computation intensive, so we see around 11% improvement. And also we try with some Puma workloads. This is some workload developed by Purdue University. There we see for different application kernels like adjacent list, self-join, ranked inverted index, sequence count, inverted index kind of workloads, we see different kind of benefits based on the application characteristics. So with this, let me conclude our presentation. So what we want to bring in this talk is, first of all, we want to explore NVM-aware RDMA-based communication and I/O schemes for big data analytics. So we propose a new library called NRCL. This is still working in progress. We want to, based on this library, we are trying to redesign the HDFS storage architecture with NVRAM. We also see there's a lot of opportunities to redesign the RDMA MapReduce or Spark or even other middlewares. So the results we feel is very promising. We believe that in the maybe next 1 or 2 years or even more near, there will be a lot of works or a lot of designs proposed in the community, and they were heavily used NVRAM plus RDMA protocol. So we are trying to, in the future, we're trying to further optimize our NRCL library. Probably we will also try if RDMA write plus the comedic semantic if it's available. And then we're also trying to co-design more big data analytics frameworks. And just the advertisement our workshop. So we have come up with some new workshop called HBVDC. So high performance big data computing. This is a focus on how you can improve the performance of current generation big data analytics stacks, because we see that current big data analytics stacks compared with HPC is still quite slow. So we were trying to use more this type of new technologies to improve it. So if some of you planning to attend IPTPS in Orlando this year, please feel free to join our workshops. Or if you want to contribute to the workshop, please let me know. Thanks a lot. I'm happy to take any questions.